Hello, and welcome to the lecture on 3.6. Today we're going to talk about rational functions. I'm going to start with recalling what a rational function is. So recall that a rational function, r of x, is one polynomial, p of x, divided by another polynomial, q of x. So as long as we have a function where we have a polynomial divided by another polynomial, our function is called rational. Rational functions and asymptotes. The domain of a rational function consists of all real numbers x except those that make the denominator 0. So I'm going to show you an example of this, and we've talked about this before as it relates to domain, but we're about to get into the asymptotes. Suppose that we have a function r of x is equal to 1 over x plus 2. What is the domain of this function? The domain ends up being that x cannot equal 2. So if we were to write that in interval notation, it would be negative infinity to 2, union 2 to infinity. And as you can see, everything except 2 is in this interval. Right? Now we're going to get into asymptotes, and we're going to come back to this problem in a second. So I need to define what asymptotes are, and we're going to start with vertical asymptotes and then get into horizontal asymptotes. Definition of a vertical and a horizontal asymptote. Now this definition is a bit hand wavy. You get a more rigorous definition in calculus, but for right now, there's not much I can do about how hand wavy this definition is. The line x equals a is a vertical asymptote of the function y equals f of x if y approaches positive or negative infinity as x approaches a from the left or from the right. This concept gets a little bit more elaboration in calculus. For now, we just have to try to understand it before we can get into some very rigorous notation. So this vertical line here is x equals a, this dotted line. Note that the vertical asymptotes are not a part of the graph, they're guidelines for your graph. So this dotted line is not actually any point on the graph. And this should make sense when we understand it a little bit more. Okay, now some notation for us. When we say that x approaches a, we write it in this notation. X is moving towards a. Now, which direction is x moving towards a? That's a question because we just said that a vertical asymptote of the function y equals f of x is that y approaches positive or negative infinity as x approaches a from either the left or the right. So either we're going to be approaching, our x values are going to be approaching a from the right or from the left. So if we're approaching from the left, then our x values are increasing up to a. And if we're approaching from the right, our x values are decreasing down to a. So it would be like plugging in numbers that get closer and closer to a. So let me show you what I mean by that. So for instance, if we said that x was approaching, let's say that x is approaching 2, and we had x here, then we would say, well, we want to look at the values 1.9, which is kind of close to 2. It's a tenth of a unit away from 2. And then our next x value would be 1.99, and then 1.999, and then 1.999. And we could do this forever. We can continually get closer and closer to 2, to the x value 2. And we'd be plugging these x values into our function f of x to determine what's happening to the y value. Remember, f of x is the same thing as the y value. So if we plugged in 1.9, what would f of 1.9 look like? What would the y value look like? If we plugged in something even closer to 2, what would the y value look like? If the y values are increasing to infinity, as x is getting closer and closer to 2, then we would say that x equals 2 is a vertical asymptote. Similarly, if the y values approach negative infinity, so they decrease without bound instead, then we would also have a vertical asymptote at x equals 2. Right? Now, in practice, graphically, what this looks like is if we're approaching a, if x is approaching a from the left, we write this little notation, this negative sign, indicating that we're on the left side of a, but we're moving towards a. This arrow saying we're approaching a. This negative sign is indicating that we're on the left side. So we're approaching a from the left. What is y doing? Well, y could be going up to infinity. And we would say then that x equals a is a vertical asymptote. Now what it looks like graphically is as x is getting closer and closer to a, the y values are increasing without bound, like this. So let's zoom in here, and I'll explain a little bit more here. So at 1.9, let's say that we were at 1.9, be about here. Our y value would be whatever this vertical distance is. Okay. If we get even closer to a, and we go 1.99, that would be 1/100th, it would be about here. And you see how our height has increased? And if we get even closer, then our height would increase even more, and so on and so forth. But the point is, as x gets closer and closer to this a value, these y values are increasing without bound, meaning that they are increasing up to infinity with no limit. But graphically, this is what it looks like when x is approaching a from the left, y is going to infinity. Now there's 3 other versions of vertical asymptotes, and I'll show you another one here. Suppose that we're approaching a from the right instead of the left. So again, this is x equals a. This vertical line has the equation x equals a. And again, it's not a part of the graph. It's a guideline for your graph. But if we're approaching a, and for simplicity, I'm going to say that my a is 2 again. This time we're approaching from the right. So our x values would be bigger than a. So we're decreasing down to a now, right? So our x value might be 2.1. Again, 1/10 of the unit away from 2, just like we started here, 1/10 of the unit away from 2. But now we're going to get even closer to 2.01. So now we're 1/100th of a unit away from 2, just like we were here. 2.001, and then 2.0001, and so on. You could, again, do this forever and ever. Now, what we're saying here is that we're on the right side of A, and our x values are decreasing down to A. That's what we're saying. And graphically, what that looks like is something like this, where our y value is going up to infinity, x goes to a from the right, y goes to infinity. This is what this would look like graphically. As x approaches a from the right side, the y value is going to infinity. Now the other two are the negative infinity versions. As x goes to a from the left, y goes to negative infinity. Instead of going up, our graph would be going down. So we would have, again, an a here. Keep it arbitrary. And as our x values are approaching a, our y values are decreasing down to negative infinity. This is what it would look like graphically. And the last one would be as x approaches a from the right. So this time we're bigger than a, and we're decreasing down to a. Y is going to negative infinity, and it would look very similar to this, the graph we just graphed, except we would be on the right side of a instead of the left side of a. So this would be a again, and we would have something that looks like this. Getting closer and closer to this vertical asymptote as our y value decreases to negative infinity. So that's what a vertical asymptote is definitionally. Now again, this is not quite rigorous because we don't really have a well-defined version of what x approaching a means and what y approaching infinity means. You get those definitions later on if you continue to take math courses. You get more rigorous definitions. Okay. The second definition that I want to talk about, because we were talking about vertical asymptotes, now I want to talk about horizontal asymptote. The line y equals b is a horizontal asymptote of the function y equals f of x if y approaches b as x approaches positive or negative infinity. So we have previously talked about end behavior. And when we previously talked about it, we had it in the context of polynomials and whether they go up to infinity or down to negative infinity. This time, we're talking about end behavior again, but in a little bit different light. We're talking about rational functions instead of polynomials. And we want to see what happens at positive infinity for this graph. Suppose we have a graph here. What's happening as x gets very, very large? We want to see what the y value is doing. As x gets really, really negative, we want to see what the y value is doing. And if it actually approaches a y equals b line, then we say that that line is a horizontal asymptote. So let me draw out a line y equals b. And again, not a part of the graph. It's a guideline for your graph. As x approaches infinity, let's say. Now, what this would look like if we were to plug in values, we would say x here, y equals f of x here. X could be 10, and then 100, and then 1,000, and then 10,000, and so on. And again, we can do this forever and ever, and let x get larger and larger and larger, and see what the y values are doing. The y values might end up being something like 2.9, 2.99, 2.999, and so on. And if this is the case, we would say that the y values are getting closer and closer to 3. Notice how this is 1/10 of a unit away from 3, then 1/100th of a unit away from 3, 1/1000th of a unit away from 3, and so on. And I'm using 3 as an example. Of course, b would be any sort of number. And what it would look like would be something like this. And our y value is capped here. So this curve wouldn't jump above the y value. It would just continually get closer and closer to this line here. Now, it is also possible that we would be coming down and we would still have a horizontal asymptote. But seeing as I use the example that we were increasing up to 3, I'm going to continue with this line. So as x approaches infinity, we might say that y is approaching b. Now, it doesn't matter which side y is approaching b from. It could be the top or the bottom. As long as it's approaching b, we would have a horizontal asymptote. Now, similarly, if we're looking as x approaches negative infinity, what is y doing? Well, y would be approaching b also, and we would have a horizontal asymptote in that case. Instead of going to the right forever, what if we went to the left forever and we saw what happened there? Oh, if our graph approaches b, then we have a horizontal asymptote. And I'll use the example coming down to b instead. So we might have x is equal to -10, -100, -1,000, -10,000, and so on. And our y values might be coming down to b. So let's say that our b is 3 again. Then this might be 3.1, 3.01, 3.001, 3.0001. And we would still have a horizontal asymptote because our y values are still approaching this b value. It's just our x values are going to the negative side instead. So we would have something that looks like this instead, where our y values are getting closer and closer to this line as our x values go to negative infinity. Now I want to ask you a question here. And this is kind of a tricky question, so just think about it. How many vertical asymptotes is it possible to have on a graph? How many times can our y value go to negative infinity at some given x value? So pause the video and take a second to think about this. The answer is actually infinitely many. For instance, when you take the trig class, you'll see that tangent and secant and cosecant have infinitely many vertical asymptotes. So we can have as many vertical asymptotes as we want. My next question, how many horizontal asymptotes can I have? And this question is actually not infinitely many. You can have 0 horizontal asymptotes, you can have 1 horizontal asymptote, or you can have 2 horizontal asymptotes. There's only 2 ways for x to go to an infinite value. That would be in the negative version and the positive version. And if y goes to a value as x goes to a negative infinity, then we have a horizontal asymptote. Maybe y goes to a different value as x goes to positive infinity. Then you would have a different horizontal asymptote. But you can't have another infinity. X will never approach a third infinity. There's only 2. You have positive infinity and negative infinity. There's only a possibility of having 2 horizontal asymptotes. So I'm going to give you a function that has 2 horizontal asymptotes. 1 divided by 1 plus e to the negative x. As x gets very large, so as x goes to infinity, then you have e to the negative infinity, which would be the same thing as saying 1 divided by e to the infinity in some fashion. Essentially this. Now e to the infinity, to the power infinity, it's not really an infinity, but it's a very, very high power. This gets very close to 0. So you would have 1, essentially you would have 1 divided by 1 plus 0. So y would approach 1 as x goes to negative infinity. What happens? Well, negative infinity will cancel this negative. So we would have, instead of having 1 divided by e to the infinity, you would have 1 over 1 plus e to the infinity. Now, e to the infinity goes to infinity. This gets very, very large. So essentially you would have 1 divided by an extremely large number, which is close to 0. So our y would be going towards 0. And you would have, as x is going to infinity, you'd have a horizontal asymptote at 1. And then as x goes to negative infinity, you have a horizontal asymptote at 0. So it looks something like this. Now I want to talk a little bit more closely about the previous example that we did. F of x is equal to 1 over x plus 2. And I want to show you how to figure out that this has a vertical asymptote at negative 2. First of all, we know that x cannot be negative 2 because it's outside the domain. The domain would be x is not equal to negative 2. So our domain would look like negative infinity to negative 2, union 2 to infinity, like this. And if you look through negative 2 to infinity, if you look through this interval, you'll see that it includes every single number except negative 2. Now here, we know that our domain is x cannot be -2. And since x can't be -2, we know that there will be no y value when x is equal to -2. Right? Now, what happens around -2 though? If we're getting close to -2, we're not at -2, so we do still have y values. So I want to see what happens to the y value as we approach -2. So we have this. We have a vertical asymptote, and I'm going to show you why. So as x approaches -2 from the left, so we're coming up towards -2, what we'd see is this. So if x is -2.01, then our y value would be 1 divided by -2.01 plus 2. So this would be -0.01, which is the same thing as -100. If we had a -2.001, same idea. -2.001 plus 2 is -0.001 in the denominator, and this is equal to -1,000. And we can continually do this, but you can already see the pattern. The y value is going to be increasing in the negative direction without bound. So as our x values get closer and closer to -2 from the left side, our y value is going to -infinity, something like this. So now let's check. Now let's check as x goes to -2 from the right. So now we're bigger than -2, but we're approaching -2. So we would have something that looks like this. Still an x and a y, and we would have -1.9. Now in the denominator, that would be 1 divided by a -1.9 plus 2, which is 1 divided by 0.1. So this is equal to 10. -1.99. Then again, this would be 1/100th in the denominator. So this is equal to 100. If you multiply top and bottom by 100, you'll eliminate the decimal, and you'll have 100 in the numerator and a 1 in the denominator. And we can do this one more time, and we end up with 1/1000th in the denominator. We get a 1000 here. So our y values go from 10 to 100 to 1000 in the span of less than 1/10 of a unit. So our y values are increasing without bound as our x values get closer and closer to -2. Right? So we definitely have a vertical asymptote. We only needed to show one side in order to have a vertical asymptote, but we definitely have one here. Y is going to infinity. Now let's determine any horizontal asymptotes. So we say, well, what's happening as x goes to infinity? Well, we can see as x is going to infinity, we would end up with 1 divided by a very, very, very large number, which is essentially 0, right? 1 divided by a massive number means that our y value here is going to be close to 0. Now, since we're above this, it's going to come down like this and get closer and closer to 0. Now, as x goes to -infinity, we get the same idea, right? 1 divided by -infinity plus 2 would be a negative massive number. So we're still on the negative side of 0 because we have a negative number here in the denominator, and we have a positive divided by a negative would be negative. But it's very, very close to 0. So this would come down and go something like this. So this graph would look something like this. But I expect you to be able to determine if we have vertical and horizontal asymptotes by going through this process here. The next thing that I want to talk about is the transformations of y equals 1 over x. Recall what 1 over x looks like. So if we take y equals f of x, where f of x is equal to 1 over x, then we have this function here. Now what we're going to do is we're going to translate this using the graph shifting techniques and stretching techniques that we used in 2.6. So let's go ahead and do an example, as we should know or remember what is in 2.6. Graph f of x is equal to 3 divided by x minus 1. Right. Now this one is one of the more straightforward ones. We can rewrite this as 3 times 1 over x minus 1. Now if you don't see the manipulations of the graph of 1 over x, then we are taking 3 times this graph, and this graph is the shifted graph of this. So f of x, or if g of x is equal to 1 over x, then f of x is equal to 3 times g of x minus 1. This. Just in case you were struggling to see the different manipulations that we have. So we're going to stretch vertically by a factor of 3, and we're going to shift f. We're going to shift 1 over x to the right 1 unit. Right? And if you remember, we stretch first, and then we shift. Now, stretching a 1 over x is primarily done at the 1, 1 spot, because 1 over x intersects the point 1, 1 and -1, -1. So this stretching by 3 units vertically will pull this up to 1, 3, and this down to -1, -3. This graph here will be the stretched version of 1 over x. It'll look like this. So this graph here is y equals 3 divided by x. Now we need to take this graph and shift it to the right 1 unit. So note that we have a horizontal asymptote at 0, y equals 0, and we have a vertical asymptote at x equals 0. So if we're shifting to the right 1 unit, the horizontal asymptote will not change because it extends infinitely horizontally. So we still have a horizontal asymptote at y equals 0. But our vertical asymptote, which was at x equals 0, is going to shift to the right 1 unit. So it's going to move to here at 1. Right? Now all of the points on the graph will also shift. So this will move over to 2, 3 instead of being at 1, 3. This point. And this point, instead of being at -1, -3, it will be at 0, -3. And this is what it looks like. Something like this. All I did was take this graph, apply a vertical stretch by a factor of 3, and a shift to the right 1 unit. And I'm going to do another example that's similar to this, but we're going to have a vertical shift as well. And it's going to look a little bit weird. So I want to graph now f of x is equal to 2x plus 1 over x plus 2. Right, now this might not look like a manipulation of 1 over x, but it is. We have to apply a little bit of processing before we can actually view it as such, but we can do that. So first thing I'm going to do in the numerator, and this is a trick that you'll pick up after doing a bunch of these problems, I'm going to add and subtract 3. Now, why am I adding and subtracting 3? 2x plus 4 minus 3. Note, adding and subtracting 3 doesn't actually change the problem, because I am adding and subtracting 3 is the same thing as adding 0. So my 1, I added 3, so I got a 4. and then I subtracted 3 so that if I wanted to, I could combine like terms and get back to the original problem, which is unchanged. But instead of that, what I'm going to do is I'm going to break up the numerator over this subtraction. So this will be 2x plus 4 over x plus 2 minus 3 divided by x plus 2. Right. Now we can look at this a little bit differently because I can factor a 2 out of the top and I'm left with x plus 2. So hopefully you now see why I added 3 here. It was so that I could get a multiple of x plus 2 on the top and bottom so that when I cancel, I end up with 2. I still have my minus 3 divided by x plus 2. And this, of course, reduces to 2 minus 3 over x plus 2. Now, looking at this, hopefully you can see that it is actually a manipulation of 1 over x. So this function turns out to be f of x is equal to, I'm going to rewrite it a little bit so that you might see it a little better, negative 3 divided by x plus 2 plus 2. This is a vertical shift of 2 units up, horizontal shift of 2 units to the left. We have a reflection about the x-axis and a stretching factor of 3. I realize that's a lot. So when we're doing these, remember, you want to do order of operations. Reflections and stretching and shrinking are at the multiplication level, so we do those first. So we take our original graph, 1 over x, which looks like this. We reflect it and stretch it by a factor of 3. So I'm going to reflect it and stretch it by a factor of 3. Normally 1 over x will look like it will be up here. But now, because I'm reflecting it over the x-axis, because of this negative, then it's going to look like it's going to be in the 4th quadrant here, and it's going to look like this. But I also am stretching by a factor of 3 vertically. Just so you know, if g of x is equal to 1 over x, then f of x is equal to a negative 3 times g of x plus 2 plus 2, like this. So if you can see it better this way, hopefully that helps see that we have a reflection about the x-axis, a stretching factor vertically by a factor of 3, and a vertical shift of 2 and a horizontal shift of 2 to the left. A vertical shift, of course, is going up. So we would have here 1, 2, 3, 1, 2, 3, where the original 1 over x graph is down here. It gets reflected and stretched by a factor of 3, so it'll be up here. So I'm doing just the reflections right now, the reflections and the stretching factor right now. And it's going to look something like this. Right? This graph is y is equal to negative 3 over x. Now I want to do the vertical and horizontal shift. So note that we have a horizontal asymptote at y equals 0. Since we're shifting horizontally, that won't affect it, but when we shift vertically, it will. So our new asymptote will be at y equals 2. Because we have a vertical shift of 2. We're going 2 units up. So y equals 2. We also have a vertical asymptote of 0, x equals 0 here. And the vertical shift of 2 won't affect a vertical asymptote because it extends forever vertically. So if we shift a line that extends forever vertically up or down, it's not going to do anything. But shifting it horizontally will change it. And we shift horizontally by 2 units to the left. So our vertical asymptote will now become x equals negative 2. Note here, our horizontal asymptote is y equals 0 over here. This is 3 units above the horizontal asymptote. So it'll be 3 units above the horizontal asymptote here. So we get 1, 2, 3. That would be this point. circle them so that we can see them where the points are shifting to. And this curve at this point is 3 units below the horizontal asymptote and 1 unit to the right of the vertical asymptote. So 3 units below and 1 unit to the right of the vertical asymptote. So this point is the same as this point. That's how it shifts. And this will be the graph. And yes, it looks different than this one, but it is actually the same graph. It's a bit tricky. All right, I want you to try a problem now. Graph the function f of x is equal to 2 divided by x minus 3. You're going to want to use the parent graph 1 over x in order to graph this. The next thing that I want to talk about is asymptotes of rational functions. So to do this one, I'm going to start with an example. Then we'll move on from this example to extend on how to find horizontal asymptotes. So let's start with example, and we're going to graph the function f of x is equal to 2x squared minus 4x, 4 divided by x minus 2 quantity squared. So something like this. As we've discussed before, in order to find vertical asymptotes, we need to look at the zeros of the denominator. So here what we're looking for is as x approaches a 0 in the denominator, does our y value go to infinity or to negative infinity? If so, then we have a vertical asymptote. If not, then we don't. And it is possible to have a 0 in the denominator and not have a vertical asymptote, but most of the time you will have a vertical asymptote. So what I'm trying to describe here is that all vertical asymptotes occur when you have a 0 in the denominator, but not all zeros in the denominators will create a vertical asymptote. Start at x is going to 2 from the left. Now, as x goes to 2 from the left, what is happening to our y value? Well, if we plug in 2 from the left, because remember, we're getting really close to 2, but we won't be at 2. Now, because we're getting so close to 2, we can essentially just plug it into the numerator, because the numerator is not undefined at 2. Right, so if we look at the y value as x approaches 2, we would see we have 2 times 2 squared minus 4 times 2 plus 4. Now we can't plug 2 into the denominator because that will make the denominator 0. We're trying to avoid that. And we're approaching 2 from the left, so we're going to be slightly less than 2. So I like to denote this by saying this is 1.99 all the way up. Some arbitrary number of 9s here. Right, we're extremely close. Minus 2 squared. So we'll plug in a number arbitrarily close to 2. On the negative side of 2, we would get in the numerator 2 times 4 minus 4 times 2, so 8 minus 8 plus 4, so we have a 4 in the numerator. And in the denominator, we have a negative 0.00, an arbitrary number of zeros, 1. We have an arbitrary number of zeros here. We get a negative 0.0001 quantity squared here. That's because we're arbitrarily close to 2. Now, from here, we can see that this negative is actually going to be squared out. Right? So we have a finite number, 4, divided by a infinitesimally small number here. So this makes our value infinitely large. So our y value, as x goes to 2, our y value is going to positive infinity. Now let's check 2 from the right, see if we get a positive or negative infinity. So now, again, in the numerator, we can plug in 2 because it doesn't make the numerator undefined. does, however, make the denominator undefined, and that's why we can't plug it into the denominator. So here we have 2 times 4 minus 4 times 2 is 8 minus 8, plus 4 is going to be 4 again. And this time we're plugging in a 2.00 with an arbitrary number of zeros, 1 minus 2 here, squared. We're plugging in something arbitrarily close to 2, but on the right side of 2. So this number needs to be slightly larger than 2, just like this one is slightly less than 2, because we're approaching from the right this time. So we get 4 in the numerator, and in the denominator we end up with 0.00 with an arbitrary number of zeros, 1 at the end, and we square that. So again, we have an infinitesimally small number here, and 4 in the numerator. So 4 divided by an infinitesimally small number will give us infinity. So as x goes to 2 from the right, our y goes to infinity. So we know a couple of things here. We do have a vertical asymptote because as x approaches 2, y is going to infinity. From either side, it doesn't matter. After this one, we knew we had a vertical asymptote. Now, the other thing that we know is that as x approaches 2 from the right, y is going to infinity, and as x approaches 2 from the left, y is also going to infinity. Okay, so we have a little bit of information for our graph. Let's write that off to the side. X approaches 2 from the left, y goes to infinity, and as x approaches 2 from the right, y also goes to infinity. Box this for later. Okay, now our question is, how do we find a horizontal asymptote? We do have a vertical asymptote at x equals 2. How do we find a horizontal asymptote? All right, well, let's look at our graph again. We have f of x is equal to 2x squared minus 4x plus 4 divided by x minus 2 quantity squared. What I'm going to do here is multiply out the denominator. I'm going to do this specifically for the horizontal asymptote. The only reason. We have 2x squared minus 4x plus 4, and then in the denominator we would have x squared minus 4x plus 4. The next thing I'm going to do is I'm going to multiply top and bottom by 1 divided by x to the highest degree term in the denominator. So we have a degree 2 is our highest degree term. So I'm going to divide top and bottom by x squared. We have this. Now when I multiply these, remember you have to distribute for everything. So f of x will then become 2x squared over x squared minus 4x over x squared plus 4 over x squared, x squared over x squared minus 4x over x squared plus 4 over. We have this. Now, remember what a horizontal asymptote is representing. It's representing the end behavior of a graph. So as x goes to infinity, what is happening to y? And as x is going to negative infinity, what is happening to y? So here, I set this up so that we can do this relatively easily. If we let x go to infinity, it's the same thing as saying that x is going to become arbitrarily large. So if we let x become arbitrarily large, we would have 4 divided by an infinitely large number, which means that this fraction is infinitely small. So as x is going to infinity, this term is going to 0. Similarly, we can cancel an x in the second term here, but we still have a 4 divided by an x. So as x gets very, very large, we still have 4 divided by an infinitely large number. So this term will also go to 0 because 4 divided by an insanely large number is essentially 0. Similarly here, we will have this term going to 0 and this term going to 0. And again, you can cancel an x here, 1 in the numerator and the denominator, still get a 0 here and a 0 here. So these four terms will go to 0 as x goes to infinity. So all we're left with are these two terms. We're left with a 2x squared divided by an x squared. Cancel this and this and this and this. And we get 2 divided by 1, essentially. This would be minus 0 plus 0. This would be minus 0 plus. So as x gets infinitely large, we have a 2 in the numerator and a 1 in the denominator. That means that y is approaching 2. Similarly, as x goes to negative infinity, the same rule applies. As x gets large, as the denominator gets large, no matter if it's a negative large number or a positive large number, as x gets large in the denominator and the numerator stays the same, this entire fraction is going to go to 0. So these four terms will go to 0 again, even when x is going to negative infinity. And then we cancel out exactly the same way, our x squareds top and bottom, and we end up with y going to 2 as well. So now we have our horizontal asymptote. As x is going to infinity, and as x is going to negative infinity, y is approaching 2. So our horizontal asymptote is y is equal to 2. Now here, the trick is to know whether or not we're going to 2 from above y equals 2 or below y equals 2. Go ahead and graph what we know right now. I'm going to graph my vertical asymptote in red, and my vertical asymptote was at x equals 2. And I'm going to graph my horizontal asymptote in blue, and that's at y equals 2. Now, our graph, which will be in black, we know from the previous page that as x approaches 2 from the left, y is going to infinity. And as x approaches 2 from the right, y is also going to infinity. So what we know about this graph is if we approach 2 from the left, our y value is going to infinity. And if we approach 2 from the right, our y value is going towards infinity. So the question is, do we ever cross this line, this horizontal asymptote, like this? Or do we come down and just hover next to the horizontal asymptote? Because remember, as x gets very large, i.e. going to infinity, we are going to be approaching this line. Our y value is going to get closer and closer to y equals 2. Right? And as x approaches negative infinity, same idea. We're going to be approaching this line. The question becomes, do we ever dip below the line, or are we always above the line? And how do we find that out? Well, there is a way to find out. So we go back to our function, f of x is equal to 2x squared minus 4x plus 4 divided by x minus 2 quantity squared. You could use the multiplied out version if you want to. We're going to end up multiplying it out again, so I would recommend using the multiplied out version for this particular process. So this entire thing, if we plug in an x, this entire thing represents our y. And we're asking ourselves, do we ever cross the line y equals 2? So what we're saying is, does this y value ever reach 2? Y equals 2. So we set 2 equal to the left, or we set our y value equal to 2, and we can determine if we ever reach that y value. And we multiply this out, so we get x squared minus 4x, 4. Multiply this entire denominator to the left, and we end up with 2 times x squared minus 4x plus 4 is equal to 2x squared minus 4x plus 4. Once we distribute this 2, then we can start subtracting. 2x squared minus 8x plus 8 is equal to 2x squared minus 4x plus 4. Subtract both sides by 2x squared, and that will just cancel. We can add 4x to both sides, and we can subtract 4 from both sides. We end up with, here we would have a negative 4x, and 8 minus 4 is, of course, 4, 0. So add our 4x and divide by 4, and we get x is equal to 1. What this is saying is y is equal to 2 when x is equal to 1. So at x equals 1, we know we are touching this line. Not only that, it's the only place where we cross this line. How do I know that it's the only place where I cross this line? What I did was I set my y equal to 2 in search of any x value that will yield y equals 2. And it so happens that the only x value that yields y equals 2 is x equals 1, because that's our only solution to this equation. So this is the only point that has a corresponding y value of 2. So we know then that this, on the right side, we never actually cross the horizontal asymptote. But on the left side, we do. We not only cross it, we only cross it one time. We can also set our x equal to 0 to determine what our y-intercept will be. And if we do that, we would have a 0 minus 0 plus 4 divided by 0 minus 2.8 squared, which is a 1. So our y-intercept occurs here. We end up with something like so this would be our curve, where we actually dip below the y-intercept. Doesn't always happen, but it does happen occasionally. Finding asymptotes. I'm going to give you some guidelines on how to find vertical and horizontal asymptotes. Let R be a rational function. R of x is equal to a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, all the way down to a1x plus a0, divided by b sub m, x to the m, plus b sub m minus 1, x to the m minus 1, way down to b sub 1, x plus b sub 0. Note that our degrees are 2 different degrees. We have a degree of n in the numerator and a degree of m in the denominator. It is possible that they are equal, but for the most part, they're not going to be. 1. Vertical asymptotes. The vertical asymptotes of R of x are the lines x equals a, where a is a 0 of the denominator with higher multiplicity than the numerator. So what I mean to say here is that it's possible for x minus a to be a factor of both the numerator and the denominator. If the denominator has a higher multiplicity for that factor, if x minus a has a higher multiplicity in the denominator than it does in the numerator, then it is a vertical asymptote. If it has a higher multiplicity in the numerator, then it's not. It just means that it's outside the domain, but it just creates a hole in the graph. As I said before, all vertical asymptotes will occur at a 0 in the denominator, but not all zeros in the denominator will yield a vertical asymptote. 2. Horizontal asymptote. Now, horizontal asymptotes are a little bit different. There's sort of conditions we need to meet in order to find them. A, if n is less than m, then R of x has a horizontal asymptote at y equals 0. B, if n is equal to m, then R of x has a horizontal asymptote y equals a sub n divided by b sub n. Notice that we had an x squared in our numerator and an x squared in our denominator. After we multiplied out the denominator, you can see we have an x squared here. So this, our B case was what we did here. And notice that our a sub n was 2 and our b sub n was 1. So what this is saying is that y would have equaled 2 divided by 1 in the previous example, which it did. We just found it a little bit different. C, if n is greater than m, then r of x has no horizontal asymptote. Now I'm going to prove this to you. You don't have to watch the proof if you don't want to. You are welcome to just skip it. Essentially, the proof is going to be exactly what we did in the previous problem, where we divide top and bottom by 1 over the x with the max degree in the denominator. So if we have a sub n x to the n plus a sub n minus 1, x to the n minus 1, all the way down to a sub 1x plus a sub 0 divided by b sub m x to the m plus b sub m minus 1 x to the m minus 1, all the way down to b sub 1x plus b sub 0. Now here, we have to remember that m is larger than n. So we take the highest degree in the denominator, which is m. We divide top and bottom by x to the m power. Again, keep in mind that m is greater than n. When we distribute this, we end up with a sub n, x to the n over x to the m, plus a sub n minus 1, x to the n minus 1 over x to the m, all the way down to a sub 1, x over x to the m, plus a sub 0, 1 over x to the m, divided by. Now we do the same thing with the denominator. b sub m, x to the m divided by x to the m, b sub m minus 1, x to the m minus 1 over x to the m, all the way down to b sub 1, x over x to the m, plus a sub 0, 1 over x. Now again, note that m is larger than n, so if we divide x to the n by x to the m, we're going to have x's that remain in the denominator. This will end up being a sub n, 1 over x to the m minus n, plus a sub n minus 1, 1 divided by x to the m minus n plus 1, all the way down to a sub 1, 1 divided by x to the m minus 1, plus a sub 0, 1 over x. And similarly here, we would have a similar thing happen in the denominator, except we have x to the m divided by x to the m. So we end up with just a 1 here. Plus, and that's the reason we divide. I'll explain that in a second. b sub m minus 1, 1 over x, all the way down to b sub 1, 1 over x to the m minus 1. All right, now notice that we have something here that does not have an x in the term at all after we divide by x to the m. Now that's the reason we want that. That's the whole key to this problem. Because now when we let x go to infinity, everything with an x in the denominator will go to 0. So in the numerator, this goes to 0, this goes to 0, this goes to 0, this goes to 0. The entire numerator goes to 0. We do not want the entire denominator to go to 0. That's why we leave a single term here without an x in it. And we need that. That's why we divide by the x to the highest degree power in the denominator, specifically the denominator. So here, as x goes to infinity, this doesn't change. This goes to 0, and all the other terms go to 0. So we end up with y going to the 0 divided by b sub m, which is equal to 0. So as x is going to infinity, our y is going towards 0. I'm just going to prove the second part too, the second point. Let m equal n. And in this case, we do the exact same process. I'm going to explain it all again, just in case you missed it in the first one. Our function would become a sub n x to the n. It's a sub n minus 1 x to the n minus 1. Way down to a sub 1x plus a sub 0 divided by b sub m, but because m is equal to n, I'm just going to use n, x to the n plus b sub n minus 1 to the n minus 1, all the way down to b sub 1x plus b sub 0. Now again, I can use n here instead of m because m is equal to n. Since they're equal, I can replace m with n or n with m. It doesn't matter. Now, again, we divide top and bottom by x to the highest degree in the denominator. The highest degree in the denominator is n. So we divide top and bottom by x to the n. Distribute it all through, and we get a sub n, x to the n over x to the n, a sub n minus 1, x to the n minus 1 over x to the n, down to a sub 1, 1 over x to the n minus 1 plus 0, 1 over x to the n, divided by b sub n, x to the n over x to the n, plus b sub n minus 1, the n minus 1 over x to the n, all the way down to b sub 1, 1 over x to the n minus 1, plus a sub 0 times 1 over x to the n. Now again, as x goes to infinity, we can see that this will cancel, but everything else, we have a higher degree x in the denominator than the numerator. So as x goes to infinity, since this will reduce to 1 over x, we'll end up with a 0. This will end up being a 0. This will end up being a 0. So this will go to 0. 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 And this. So all we have left is a sub n divided by b sub n. So y will approach a sub n over b sub n. I want you to try a problem. Find the vertical and horizontal asymptotes for the function f of x is equal to 3x squared minus 4x plus 12 divided by x squared minus 8x minus 15. Right, the next topic I want to talk about is graphing rational functions. So right now I'm going to give you a guideline on how to graph rational functions. 1. Factor the numerator and denominator. 2. Find the x and y intercepts. Now the x-intercepts will always be a 0 in the numerator, but again, not all zeros in the numerator will give you an x-intercept. And we'll explain this in the next subsection. Y-intercepts, you just plug in 0 for x. 3. Find the vertical asymptotes. Now, vertical asymptotes, again, are always going to be a 0 in the denominator. And again, not all zeros in the denominator will be a vertical asymptote. So when you're looking for vertical asymptotes, you're looking as x goes to some number, is y going to infinity or negative infinity? That's the key for this, because that's the definition. 4. Find horizontal asymptotes. Horizontal asymptotes is just as x goes to positive or negative infinity. What is the y doing? You'll consult this chart here to determine what your horizontal asymptote is. If n is bigger than n. If the numerator has a lower degree than the denominator, you have a horizontal asymptote of y equals 0. If the degree of the top and the bottom are equal, then it's the leading coefficient of the top divided by the leading coefficient of the bottom. And of course, if the numerator has a higher degree than the denominator, there is no horizontal asymptote. 5. Sketch the graph by using the info here. So you'll find all of this information, plot it all out on a graph, and then draw a path that connects all of the information. Let's go ahead and do an example. Graph f of x equal to x minus 3 times x plus 1 divided by x plus 2 times x plus 4. Okay. Note I've already factored it, so step 1 is down. We've already done step 1. So we need to find our x and y intercepts, our next step. Remember, x-intercepts are when y is equal to 0. So we would set our entire function equal to 0. Notice here, by plugging in values of x, the only way for this fraction to be 0 is if there's a 0 in the numerator. Okay? I can plug a 0 into the denominator all day. I can plug any number into the denominator. If the numerator is not 0, then we won't have a 0. This fraction, this division, will not result in 0. So the only way that we can have a 0 is if we plug zeros in here. Also note, another way of looking at this is we can multiply this side to the denominator to the left side, and you would have 0 times this denominator. Now there is a key piece of information that gets lost, and that key piece of information is exactly why not all zeros in the numerator will result in an x-intercept. And I want you to try to think about what that is, but we'll cover it in the next subsection. So don't worry if you can't figure it out. But here, we're just looking at the zeros of the numerator. So if x is equal to 3, we would have 0 times whatever this is divided by whatever these are, and you would get 0. If x is equal to -1, you would have 0 times whatever this is when x is equal to -1, divided by whatever these are when x is equal to -1, and you would get 0. So our x-intercepts are 3, 0, and -1, 0, just like that. And of course, our y-intercepts, we just plug in at 0 for x. We would have f of 0 is equal to 0 minus 3 times 0 plus 1 divided by 0 plus 2 times 0 plus 4. Will give us a -3 divided by 8. So our y-intercept is 0, -3/8. Now when you graph these, they don't have to be perfect. So don't freak out if you don't get it exact. We're just sketching here. Right. After x and y intercepts, we look for vertical asymptotes. Again, you'll look at the zeros in the denominator. Now, in this case, both zeros of the denominator will become vertical asymptotes. And again, I'll explain that in the next subsection as well. The possible vertical asymptotes that we have are x equals -2 and x equals -4. So, if we approach -2 from the left, what happens to y? Oh, if we plug in a -2, something very close to -2, but on the left side, we would have -2 essentially here, -2 plus 1. This would be the numerator divided by. Now I can't plug in a -2 because I would get a 0. So I'm going to plug in something to the left of -2 because that's how we're approaching -2. So this would be -2.00 with an arbitrary number of zeros minus, or plus 2, I mean, here, just like this. And then we can plug a -2 in here, so we just use a -2. Now in the numerator, we end up with a -5 times -1, so 5. And in the denominator, we see that we have -2.000 with an arbitrary number of zeros, 1 plus 2, and we end up with a negative, arbitrarily small number times 2. And since we can see that 5 divided by an arbitrarily small number is going to be infinity. Now, is it positive or negative? And that's the key part when we're looking for vertical asymptotes. Here, we have a negative times a positive, and we have a positive in the numerator. So we have a positive number divided by a negative number. This will go to negative infinity because we have a positive divided by a negative. So as x goes to negative 2 from the left, y is going towards negative infinity. Let's do x goes to negative 2 from the right, just to determine what the graph will look like as we approach negative 2 from the right. So again, negative 2 minus 3 in the numerator, negative 2 plus 1 in the numerator, and then this would be negative 1.99 all the way down to 9 here, times negative 2 plus 4. Again, we would have a negative 5 times a negative 1, 5. And in the denominator, mess this up. So the denominator here, this would be negative 1 with an arbitrary number of 9s, plus 2. I forgot my plus 2 here. This would be a very small but positive number. And then here, we would have negative 2 plus 4 is, of course, 2. Now, hopefully you can see why this is positive. This negative number is smaller than 2. So if we're adding 2 to this number that's arbitrarily close to negative 2, then we would get a positive number. So we have a positive divided by an arbitrarily small positive number. This will go to positive infinity. So again, as x goes to negative 2 from the right, y goes to positive infinity now. So on the left side of 2, our y value is going to negative infinity, but on the right side of 2, our y is going to positive infinity. Now let's check at negative 4. So x approaches negative 4 from the left. So again, because these are not 0 when x is equal to negative 4, I'm going to go ahead and plug them in. Negative 4 minus 3 times negative 4 plus 1. That's the numerator, divided by negative 4 plus 2 times something just to the left of negative 4. So negative 4.0 with an arbitrary number of zeros, plus 4 here, just like this. So again, since this is a little bit further from 0, we would end up with a negative value. We have a negative 4 times, or minus 3 is negative 7, times negative 3 would be 21, divided by negative 4 plus 2 is a negative 2, and a negative 4.0001 plus 4 would be an arbitrarily small but negative number. So we would have 21 divided by an arbitrarily small positive number because we have a negative times negative. This will go to infinity. So as x goes to negative 4 from the left, y is going to positive infinity. So we do this again, but from the right this time. So negative 4 minus 3 times negative 4 plus 1. This is the numerator, divided by negative 4 plus 2 times, now we're on the right side of 4, so it's going to be negative 3.999 with an arbitrary number of 9s plus 4. And negative 3.9999 plus 4 is going to be a positive but arbitrarily small number. So we get, again, 21 in the numerator divided by a negative 2 here times a positive but arbitrarily small number. This. So now we have 21 divided by a negative arbitrarily small number because we have a negative times a positive. So we get that this is negative infinity now. So as x goes to negative 4 from the right, y goes to negative infinity. Okay. Now this information here is very helpful on a graph, so I recommend doing this for all of your vertical asymptotes. Now our horizontal asymptote, we'll need to multiply everything out for. So as x is going to infinity, what is happening? Well, if we multiply this out, we end up with x squared minus 2x minus 3 in the numerator, and x squared plus 6x plus 8 in the denominator. Now we look at our degrees. We have an equal degree. So we're going to have a horizontal asymptote of the leading coefficient of the numerator divided by the leading coefficient of the denominator. We go back here, we see that our leading coefficient is 1 in the numerator and 1 in the denominator. So we have y is going towards 1 as x is going to infinity, and as x goes to negative infinity, y is also going to 1. Whenever you have a rational function like this, you're not going to have two horizontal asymptotes. You'll always only have 1 or 0. So we found the vertical asymptotes, we found the horizontal asymptotes, we found the x and y intercepts. It's time to graph. So we found a vertical asymptote at -2. We have a vertical asymptote of x equals -2. That's for both of these. Both of these, we have a vertical asymptote of x equals -4. And we have a horizontal asymptote of y equals. So I'm going to do my horizontal asymptote in blue. Do my vertical asymptotes in red. It's important to use the information that we found as x approaches -2 from the left. So as we approach this line here, but on the left side of this line, our y value is going to negative infinity. Let's go ahead and graph what that looks like. We're going to have something like this. As x approaches -2 from the right, our y value is going to positive infinity. So as we approach this red line again, but this time on the right side, our y value is going to positive. Similarly, as x goes to -4 from the left, y is going to infinity. So on the left side of this red line, we're going to positive infinity. And as x approaches -4 from the right, y is going to negative infinity. So again, this line, but we're going to negative. So we can already see our graph shaping up a bit, just a bit. Now let's look at our x-intercepts, 3, 0, and -1, 0. So plot those. 3, 0, 1, 2, 3, 0, and -1, 0. So it actually looks like this part will dip down and then come back up. And let's make sure that that is the case. So here we should be intersecting the line y equals 1 between -2 and -1. 1 equals, so this is me plugging in 1 for y. Remember, we have f of x is equal to this. So my f of x value is my y value. I'm plugging in a 1 for that y value. Determine when my graph hits the line y equals 1. X squared minus 2x minus 3 divided by x squared plus 6x plus 8. Now we expect that an x value will be between -2 and -1 because we're going to positive infinity here, but we're below the line y equals 1 here. So it needs to come down and intersect this line somewhere. It might do it more than once, who knows? We'll see. Multiply this over, and we get x squared plus 6x plus 8 equal to x squared minus 2x minus 3. And we can cancel our x squareds. And then we can add our 2x over, subtract our 8. And we end up with 8x is equal to -11. So x will equal -11 divided by 8. Now this number is between -1 and -2 because the numerator is larger than the denominator but less than 2 times the number, the denominator. So at negative 11 over 8, that would be about here. We cross this line. And I also need to plot my y-intercept. I haven't done. 0, negative 3/8. 0, negative 3/8. Just below half. So I have everything on the graph that I can find. Now I just need to connect the dots. Down. So it looks like this. Now I know that this does not go up above 1 again because we only have one solution to where it crosses the line y equals 1, and that's at negative 11 over 8, which means this is the only point where we cross the horizontal asymptote. We also see that we don't have any x-intercept between negative 2 and negative 4, which means that this never actually touches the x-axis, let alone going above the horizontal asymptote. And then this one, again, will never cross the horizontal asymptote, so we end up with something. And that will be our graph, right? Now, again, it's important to go through all of this information so that you have information that you can plug into your graph. So we have the point here was from here. These two are my x-intercepts from here and here. My y-intercept right here. And then all of this information are all of these arrows. These information. And then of course you have a vertical and horizontal asymptote. And I want you to try one now. Graph f of x equal to x divided by x plus 2 times x minus 2. The next thing I'm going to talk about is common factors in the numerator and denominator. Note, when the numerator and denominator share a factor, a hole is created in the graph. Let me do an example of this really quickly. Suppose we want to graph the function f of x is equal to x minus 2 divided by x squared minus 4. So the first step would be to factor the numerator and denominator. So f of x is actually equal to x minus 2 divided by x plus 2 times x minus 2. Now I want to note something here, so I'm going to do the domain. Remember, the domain is x is not equal to 2 or negative 2, because I can't divide by 0. So if I plug in a 2, I would be dividing by 0, even though I have a common factor in the numerator. So I have, even though these cancel, I still have my domain where x cannot be 2 or negative 2. So my function, for all intents and purposes, will be 1 divided by x plus 2, except at x equals 2. When x is equal to 2, we'll have a hole in the graph. So let's go ahead and find the x and y intercepts. There are no x-intercepts because the numerator can never be 0. Y-intercept is, of course, 1/2. We're plugging in 0 for x, you get 1/2. So you have 0, 1/2 as the point. Vertical asymptote. This will be any 0 in the denominator, and then we need to check to make sure. So we have x is equal to negative 2 is a 0 in the denominator. Let's make sure that it is actually a vertical asymptote. We do this by saying let x go to negative 2 from the left and from the right. We're going to start with the left. So if we plug in a number that is left of negative 2, we would end up with 1 divided by negative 2.001, an arbitrary number of zeros, plus 2 here, just like this. And this will, of course, become 1 divided by negative 0.0 with an arbitrary number of zeros, 1. So this is an arbitrarily small but negative number. We have 1 divided by this arbitrarily small number, which will give us a negative infinity. So our y value is going to negative infinity as x is going to negative 2 from the left. As x goes to negative 2 from the right, so now we're on the right side of negative 2, we would plug in something just to the right of the negative 2, which would be negative 1.9, arbitrarily close to negative 2, but on the right side. So now we have a arbitrarily small but positive number. This. And this will go to positive infinity, just like this. So as x is going to negative 2 from the right, our y value is going to positive. Now our horizontal asymptote, you should be able to see that we have a degree that is higher in the denominator than the numerator. So our denominator has a higher degree than the numerator, which means that our horizontal asymptote is y equals 0. We can show this by letting x go to infinity, but it's unnecessary. So let's go ahead and graph it now. You have to be careful and not forget that our domain is important. Remember, our domain is x is not equal to 2 or negative 2. We have a vertical asymptote of x is equal to negative 2. That vertical asymptote. Let's go ahead and draw that. And I have a horizontal asymptote of y equals 0. We already know that we don't cross the horizontal asymptote, because if we did cross the horizontal asymptote, we would also have an x-intercept, and we don't have any x-intercept. So let's go ahead and graph. As x approaches negative 2 from the left, so we're approaching this red line, but on the left side, our y is going to negative infinity. So we have our graph is going down like this. As x approaches negative 2 from the right, so we're approaching this red line, but on the right side of it, our y value is going to positive infinity. We have a line that's going up like this. Now, our y-intercept is 0, 1/2. This. And this is what it looks like. So as our curve comes down, come through this at the y-intercept, come out, and don't forget, our domain is x is not equal to 2 or negative 2. So at 2, we have a hole in our graph. And then this comes up like that. So whenever we have a common factor in the numerator and denominator, we're going to have a hole in our graph somewhere. Not necessarily whenever. It is possible that you won't have a hole, but that would mean that the hole occurred at a vertical asymptote. So if my graph, for instance, if my graph instead was x minus 2 divided by x plus 2 times x minus 2 squared, we would cancel one of the x plus 2's, but we would still have a vertical asymptote at 2. So instead of having a hole, we would actually have another vertical asymptote. And this would either go up or down, and then we'd have a curve that comes up or down on the right side of the vertical asymptote as well. But that's not what we had, so I'm going to erase that. Just a quick explanation. The last topic that I want to cover is going to be slant or oblique asymptotes. Recall. R of x equals P of x divided by Q of x is a rational function. Specifically that P of x and Q of x are polynomials. If the degree of P of x, the numerator, is 1 more than the degree of Q of x, the denominator, then R of x has a slant asymptote. Now this doesn't violate this property here. If the degree of the numerator is larger than the degree of the denominator, we don't have a horizontal asymptote. Instead, we have sometimes a slant asymptote, which is when the degree of the numerator is exactly one more than the degree of the denominator. If r of x has a slant asymptote, then r of x is equal to ax plus b plus r of x divided by q of x, and the slant asymptote is y equals ax plus b. If you remember, when we divide polynomials, we end up with a remainder, r of x, and that r of x would still be divided by q of x. Now, what's left when we have a single degree higher in the numerator than the denominator, when we divide the two polynomials, we'll end up with a linear function like this, ax plus b, plus some remainder divided by q of x still, where r of x has a lower degree than q of x. Okay. Now, this is an important note because a slant asymptote is still looking at the end behavior of the function, just like a horizontal asymptote would, except the slant asymptote will be a line instead of a horizontal line specifically. So here, when we look at the end behavior of a graph, remember we're sending x to positive infinity and x to negative infinity to see what happens. So when we have something that looks like this, where r of x is going to be p of x divided by q of x, which would result in this, where r of x, little r of x, has a lower degree than q of x, and we let x go to infinity, this entire term will go to 0 as x goes to infinity, because the denominator has a higher degree. And this would be what was left. And this is exactly the reason that this is the slant asymptote. Okay. It's a little bit tricky, but I'll explain it when we do our example here. Graph f of x is equal to 2x squared plus x minus 1 over x minus 2. So notice first, the degree of the numerator is exactly one more than the degree of the denominator. We can start with our vertical asymptote, which is going to be at x equals 2, and we can show that by saying what happens as x goes to 2 from the left. If x is approaching 2 from the left, then we would have 2 times 2 squared plus 2 minus 1 all over 1.99 with an arbitrary number of 9s minus 2 in the denominator. So I just plug in 2 in the numerator, but because I can't plug in 2 in the denominator because we would be dividing by 0, I instead plug in something that is just to the left of 2. Arbitrarily close, though. So in the numerator, we end up with a 1 here. 2 minus 1 is 1. And then 2 squared is 4, and 4 times 2 is 8. So 8 plus 1 is 9. Divided by, and then here, 1.99 minus a 2 would give us a negative value. Negative, arbitrarily small value. We end up with this. Now, this means that our y is approaching negative infinity. Negative, because the denominator is negative and the numerator is positive. So if we approach 2 from the right, we might get positive infinity or negative. In this case, it'll be positive. 2 times 2 squared plus 2 minus 1 all over 2.00 with an arbitrary number of zeros minus 2. We'll end up again with 9 and then an arbitrarily small but positive value. And this would go to positive infinity. So as you can see, we do have a vertical asymptote of x equals 2. We don't have a horizontal asymptote because the degree of the numerator is larger than the degree of the denominator. But we will have a slant asymptote instead because the degree of the numerator is exactly one more than the degree of the denominator. So I'll show you how to do the slant asymptote in a second, but that's going to take the place of our horizontal asymptote. To our x-intercept. X-intercepts would be setting this equal to 0. We have 0 is equal to 2x squared plus x minus 1 over x minus 2. And this ends up factoring into 2x minus 1 times x plus 1. Now, this function is the same as this function, and we're looking for where this function is equal to 0. So we look at here, we look at the numerator. So we look at the numerator, and we determine when the numerator is equal to 0. We end up with x is equal to 1/2, and x is equal to -1. So these are our two x-intercepts. Right, y-intercept. Now we just plug in 0 for x, and we get that y will equal 2 times 0 squared plus 0 minus 1 over 0 minus 2, which is -1, or is positive 1/2. We have a -1 and a -2. That's all that's left. So our point is going to be 0, 1/2. So we have our vertical asymptote, we have our x-intercepts, and we have our y-intercept. The next thing that we need to figure out is the slant asymptote. So I'm going to take my function, just this, and I'm going to do the division. This is how you find your slant asymptote. We do x minus 2 into 2x squared plus x minus 1. Now, you will notice that because the degree of the numerator is exactly 1 more than the degree of the denominator, when we do this division, we'll end up with a linear function. We will only have an x here. We're not going to have an x squared or an x cubed or anything higher, only an x, or some constant times x. And again, that's because the degree of this, to get from a degree 1 to a degree 2, we need to only multiply by a single x, not an x squared or an x cubed. So here we're saying, what times x gives me 2x squared? That will be 2x. 2x times x gives me 2x squared. 2x times -2 is -4x. Don't forget to subtract. 2x squared minus 2x squared cancel, and we did that by design. Then we have x minus a -4x. So we have 5x here. We carry this 1 down. Now, what times x gives me 5x? Plus 5. So 5 times x is 5x. 5 times -2 is -10. And we subtract. Don't forget to distribute your negative. 5x minus 5x is 0. And then -1 minus -10 is 9. So we end up with 2x plus 5 plus 9 divided by x minus 2. Now remember what I was saying back here, where r of x, our remainder, has a lower degree than q of x. Notice that our r of x, our remainder, 9, has a lower degree than our q of x. So again, when we're looking at end behavior of a graph, we are letting x go to infinity, and we're seeing what is the trend of y. What is y doing? Is it going up to infinity? Is it going up to infinity at a really fast rate, or is it going up to infinity at a slower rate? Is it not going to infinity, going to a finite number? That's what we're looking for. So as x goes to infinity, for this particular function, because our function y equals 2x squared plus x minus 1 over x minus 2 is equal to 2x plus 5 plus 9 over x minus 2. So notice that this is identical to this. These two are identical. They're the same thing. All I did was do the division. Now, as x goes to infinity, this part will drop out, and our y will have this trend. All right, it'll get closer and closer to this line. It'll never be equal to this line, because this will never actually be 0. It'll get closer and closer to 0, basically making it negligible. So this will be infinitesimally small, but will be trending along this path, which is 2x plus 5, which is a linear function. So our y will be going toward 2x plus 5. So this is our slant asymptote. This, when we draw our graph, at the ends of the graph, this is the line that we're going to follow. I'll show you what I mean in a second. Now let's draw everything that we know. We have a vertical asymptote at x equals 2. And we know which way we trend. So as we approach 2 from the left, we're trending to negative infinity. Our y value is trending to negative infinity. As we approach 2 from the right, our y value is trending towards infinity. Let me go ahead and draw my vertical asymptote. And when we approach the left, as we approach from the left, our y value is going to negative infinity. We have something like this. As we approach from the right, our y value trends to positive infinity, so we have something like this. This is markers for our graph. We also do not have a horizontal asymptote, so we can ignore that step for now. And then we have our x-intercept at 1/2, 0 and -1, 0. Plot those 2 points. 1/2, 0 and -1, 0. Then we also have our y-intercept at 0, 1/2. Now let's go ahead and draw our slant asymptote. There's nothing else left to do except for draw that. So 2x plus 5. I'm going to plot that curve, but I'm going to do it in blue because it's an asymptote. It's like a horizontal asymptote. It's just not flat. 2x plus 5. Okay, so I fixed my graph up a little bit. This is what we have. Now I want to know if we're ever going to cross this slant asymptote. How do I do that? Well, if we do cross, then our function 2x squared plus x minus 1 divided by x minus 2 will equal the slant asymptote somewhere. Let's check. 2x plus 5, set that equal to, that's our slant asymptote, set that equal to our function to see if our function ever actually touches this line. If we get an x equals something, then it will. So 2x plus 5 is equal to 2x squared plus x minus 1 all over x minus 2. Multiply this over with 2x plus 5 times x minus 2 equal to 2x squared plus x minus 1. Boil this out. 2x squared minus 4x plus 5x minus 10. It doesn't look like we'll have a crossing point. 2x squared cancels. This would be a single x, and we can cancel this x with this x over here. And we end up with an equation, -10 is equal to -1. Now, this equation is, of course, never true, ever. -10 is never equal to -1. What that means is that this line is never equal to this function, which means we have no intersecting points. So our curve will go up to infinity here, come down, and then it'll follow this slanted line here. And this curve will follow this slanted line and come down like this. So just like a horizontal asymptote, our curve will actually follow that line. Just in this example, and in any example where we have a slant asymptote, our line is not flat. That's all. It's just not horizontal. It's at an angle. All right, that's going to be it for today. I will see you all in the next lecture.